Hi, I'm Prabhpreet Singh, and the topic which we have chosen for our term project is the limitations of AI. Artificial intelligence has emerged as a promising field, expected to entirely change the way we interact with the world. Today, AI technologies power almost every walk of our life, from healthcare and agriculture to cybersecurity and transport systems. The emergence of artificial intelligence and its influence has led many to call it the next electricity. Hence, as students of artificial intelligence, it becomes important for us to analyze and reflect upon the practicality of such comparisons, keeping in view the ongoing technological advancements. The fundamental question revolves around whether human engineers give intelligence to the system or whether the systems are capable of learning to be intelligent. On 23rd December 2019, the very famous AI debate took place between Yoshua Bengio and Gary Marcus at Miller. Gary Marcus, who is a cognitive scientist and a professor emeritus at the New York University, argued that while AI has seen incredible leaps in recent years, thanks to the rise of deep learning, much of the AI developments are still narrow. He questioned the role of deep learning, especially using neural networks to model cognitive sciences, and the absence of any rules. He argued that the neural networks are not so good at generalizing rules, which human beings can easily do. If something has not been fed into the training space, they face a problem in trying to generalize data they have not seen. Infants can generalize outside the training space, whereas many neural networks cannot. Such models, he argued, simply cannot capture the flexibility and power of everyday reasoning, as there is no way in these systems to represent, say, what a ball is, or what a bottle is, and what these things can do to one another. So while the results look great, they are typically not very generalizable. So, does the solution lie in data? Marcus argues that data alone is not a solution. The real problem there is that these systems have a tendency to perpetuate biases that were there for historical reasons. It is not obvious that synthetic data is the solution, as opposed to building systems that are sophisticated enough to understand the cultural biases that we are trying to replace. Hence, he argued that AI's shortcomings are inherent to the technique. Researchers must therefore look beyond deep learning, he argues, and combine it with classical or symbolic AI systems that encode knowledge and are capable of reasoning.
Hi, I'm Koustav Chowdhury and I'm here to speak on the topic of artificial general intelligence and intelligence explosion. So, what exactly is artificial general intelligence? Artificial general intelligence, or AGI, is the hypothetical intelligence of a machine that has the capacity to learn and understand any intellectual task that a human being can. It is the primary goal of some AI research and a common topic of science fiction and future studies. AGI can also be referred to as strong AI. Various criteria for intelligence, such as a Turing test, has been proposed, but to date, there is no single definition that satisfies everyone. The Turing test, originally called the imitation game by Alan Turing, is a test of a machine's ability to exhibit intelligent behavior equivalent to a human being. Broadly speaking, we can say intelligence can be judged on parameters such as reasoning, learning, planning, knowledge, communication, perception, and kinesthetic. Before moving on to the topic of intelligence explosion, let us define what is a technological singularity. A technological singularity is a hypothetical point in time at which technological growth becomes uncontrollable and irreversible, resulting in unforeseeable changes in human civilization. Intelligence explosion is a possible outcome of humanity building AGI. AGI would be capable of recursive self-improvement, leading to rapid emergence of artificial superintelligence or ASI, limits of which are unknown, shortly after the technological singularity has been achieved. This idea has been conceived by a statistician known as I.G. Good. So, do we need to be worried? Frankly, no. Today's AI is speculated to be decades away from AGI. The thesis that AI poses an existential risk has been endorsed by many public figures. Perhaps the most famous of them are Elon Musk, Bill Gates, and Stephen Hawking. Many of the scholars who are concerned about the existential risk believe that the best way forward would be to teach the recursively improving AI to behave in a friendly rather than destructive manner after it reaches superintelligence. But like Andrew Van says, it's like worrying about overpopulation on Mars when we have not set foot on the planet yet.
My name is Prakhar Bindal, and today I'm going to talk about AI completeness and complexity theory of AI. Since its inception in the 1950s, the field of artificial intelligence has produced some unparalleled accomplishments while at the same time failing to formalize the problem space it is concerned with. The theory of AI completeness is basically a formalism designed to do for the field of AI what notion of NP completeness did for the computer science in general. It is a common belief that such formalization will allow for even faster progress in solving remaining problems in humankind's conquest to build an intelligent machine. Solving an AI complete problem is equivalent to general aptitude of human intelligence or basically strong AI beyond the capabilities of a purpose specific algorithm. AI complete problems are hypothesized to include general computer vision, natural language understanding, and dealing with unexpected circumstances while solving any real world problem. AI complete problems cannot be solved with current computer technology alone and will also require human computation. Now let's move to the complexity theory of AI. The complexity of executing an algorithm within a human assistant Turing machine is given by a pair psi h, psi m, where psi h basically represents the complexity of the human's part and psi m basically represents the complexity of the machine's part. One very interesting topic to discuss in the complexity theory of AI is the notion of human oracle functions. From people with mental disabilities to genius, human minds are cognitively diverse, and it is well known that different people exhibit different mental abilities. We define a notion of a human oracle function, HO, capable of computing any function computable by the union of all human minds. In other words, any cognitive ability of any human being is repeatable by our HO, which is a human oracle function. Now let's move on to the topic of classification of AI problems. Now here we have some definitions regarding various type of AI problems. The first one is the AI complete problems. A problem C is said to be AI complete if it has true properties. First one, it is in the set of AI problems which are human oracle solvable problems, and any AI problem can be converted into C by some polynomial time algorithm. The second definition is the definition of AI hard problems. A problem H is AI hard if and only if there is an AI complete problem C that is polynomial time Turing reducible to H. Now, the last definition is the definition of AI easy problems. The complexity class AI easy is a set of problems that are solvable in polynomial time by deterministic Turing machine with an oracle for some AI problem. In other words, a problem X is AI easy if and only if there exists some AI problem Y such that X is polynomial Turing reducible to Y. This means that given an oracle for Y, there exists an algorithm that solves X in polynomial time. The given figure on the right illustrates the relationship between different AI complexity classes. Right side illustrates the situation if it is ever proven that AI problems is equal to AI complete problems. Left side shows the converse. Now let's move on to the topic of beyond AI completeness. The human oracle function assumes that the human being behind it has some assistance from the computer in order to process certain human unfriendly data formats. For example, a binary string representing a video is completely impossible for a human being to interpret, but could easily be played by a computer program in the intended format, making it possible for a human to solve a video understanding related AI complete problem. It is obvious that a human being provided with access to a computer, perhaps with an internet connection, is a more powerful intelligence compared to an enhanced in such a way human. Consequently, it is more important to limit help from a computer to a human worker inside a human oracle function to assistance in the domain of input-output conversion, but not beyond, as resulting function would be both AI complete and computer complete. This figure basically a Venn diagram to illustrate the subdivisions of problem space produced by different types of intelligent computational devices. Region 1 represents what is known as a universal intelligence or super intelligence, which is basically a computational agent which outperforms all other intelligent agents over all possible environments. Region 2 is the standard unenhanced human level intelligence of type capable of passing a Turing test but at the same time incapable of computation involving large numbers or significant amount of memorization. Region 3 is basically what is currently possible to accomplish by the state of art AI programs. Finally, region 4 represent an abstract view of animal intelligence. AI intelligence researchers strive to produce universal intelligence, and it is likely to happen given recent trends in both hardware and software developments and theoretical underpinning of Church Turing thesis. It is also likely that if we are able to enhance human minds with additional memory and port those to a higher speed hardware, we will essentially obtain a universal intelligence. Conclude, I would like to say that the progress in the field of artificial intelligence requires access to a well-defined problems of measured complexity. The theory of AI completeness aims to provide a base for such formalization. Showing certain problems to be AI complete or AI hard is useful for developing novel ways of telling computers from humans. Also, any problem shown to be AI complete would be a great alternative of testing an artificial intelligent agent to see if it attained human level intelligence. Thank you.
Hi, I'm Jyoti Agarwal. I'm going to speak on the topic strong AI. Strong AI is a term used to describe a certain mindset of artificial intelligence development. Strong AI's goal is to develop artificial intelligence to the point where machines' intellectual capability is functionally equal to a human's. Next. So, in 1980s, philosopher John Searle coined this term, strong AI, as a part of his Chinese room argument, which was that suppose AI research succeeds in constructing a computer that behaves as if it understands Chinese. It takes Chinese characters as input and by following the instruction of computer program produces a response. Suppose that this computer performs this task so convincingly that it comfortably passes the Turing test. That is, it convinces a human Chinese speaker that the program is itself a live Chinese speaker by making an appropriate response to each question asked. The question Searle wants to answer is this: does the machine literally understand Chinese? Or is it just simulating the ability to understand Chinese? Searle calls this ability of literal understanding of Chinese as strong AI, and the simulation of this ability as weak AI. The definition depends on the distinction between simulating a mind and actually having a mind. Searle writes that, according to strong AI, the correct simulation really is a mind. According to weak AI, the correct simulation is a model of mind. So, nowadays, we have chatbots and that can simulate a conversation with a user in a natural language through messaging applications, websites, mobile apps, and through telephone. There are several fundamental differences between chatbots and the two examples of strong AI. Chatbots are built for the sole purpose of conversation, using increasingly complex algorithms and response databases to determine an appropriate reply to a query or a statement. They are an example of applied AI or weak AI, where systems are built specifically for one's usage. Ideally, strong AI machine, however, would be built in a form of a man, have the same sensory perception as a human, and go through the same education and learning process as a human child. Essentially, the machine would be born as a child and eventually develop to an adult in a way analogous to human development. Strong AI problems are symbolic attempt to create human intelligence in computers. Instead of trying to give the computer adult like knowledge from the outset, the computer would only have to be given the ability to interact with the environment and the ability to learn from those interactions. Turing has been the Turing test has been interpreted in a way to define intelligence. That is, if one cannot tell a computer from a human being, then it's intelligent. However, Turing himself countered that an intelligent entity can fail the Turing test because it cannot successfully imitate a human being. His response sums up the reason for Turing test, increasing relevance in AI development. Turing offered his test to question the preconceived notion that computers cannot be intelligent by providing a scenario in which computers are indistinguishable from humans. At present, AI development is overshadowed by immediate applications of applied AI, as that yields more tangible and quantifiable results. However, it can be argued that single largest stumbling block to strong AI is lack of definition of intelligence. Strong AI's ultimate goal is to make an intelligent computer that can think and understand. But those terms remain ambiguous and undefinable. Hence, there is no general measure of success in the field of strong AI. The concept of intelligence varies from person to person, and as a result, a standardized test, like a Turing test, becomes less important. So, thanks.
Hello everyone, I am Chaitanya Bhutada and I will be discussing about Moravec's paradox. Moravec's paradox is the observation by artificial intelligence and robotics researchers that, contrary to traditional assumptions, reasoning, which is high level in humans, requires very little computation, but sensory motor skills, which is comparatively low level in humans, requires enormous computational resources. As Moravec's writes, it is comparatively easy to make computers exhibit adult level performance on intelligent tests or playing checkers, and difficult or impossible to give them the skills of a 1 year old when it comes to perception and mobility. One possible explanation of the paradox offered by Moravec is based on evolution. All human skills are implemented biologically using machinery developed by the process of natural selection. A compact way to express this argument would be: we should expect the difficulty of reverse engineering any human skill to be roughly proportional to the amount of time that skill has been evolving in animals. Therefore, we should expect skills that appear effortless to be difficult to reverse engineer, but the skills that appear to require effort may not necessarily be difficult to engineer at all. To see why this is, let's take an example of toddler building tower of blocks. We call our program builder. This builder starts with a command build. As build is a complicated command, we broke down it into begin, add, and end. Add is further broken down into find, get, and put. Find is broken down into see. See is basically understanding the object is actually a block and not something else. Grasp. While grasping, we should not grasp a block which is already in the tower and which will lead this to toppling of the tower. While moving, we should not move the block in such a way that it topples the existing tower. So what if the tower starts to sway? Our builder program must have some basic physics knowledge to understand why and what to do in this situation. When we look closely, we get bewildering level of questions that do not have a straightforward answer. Let's compare it with a game of chess. We put the rules and current positions and get the best possible moves out. Same as Aristotle's method of getting the third fact from two facts. So sure, we are putting in a lot of positions, and turning of the crank is very complicated set of instructions, but we provide all the instructions and information. So more examples of Moravec's paradox is recognizing a face moving around in the space, judging people's motivations, catching a ball, recognizing a voice, setting appropriate goals, paying attention to things that are interesting, anything to do with perception, attention, visualization, motor skills, social skills, and so on. Thank you.